Hi everyone, I'm Aditya Akella from the University of Wisconsin-Madison, and I can't see my screen. Okay. And I'm going to talk today about traditional control planes. This is not exactly software-defined networking, but this will have implications for SDN, as I'll hint at towards the end of the talk. This is joint work with my students Aaron and Rajay and our collaborator Ratul from Microsoft Research. Okay, so like I said, this is about traditional control planes. So a control plane essentially is a collection of routing protocols that defines the forwarding behavior of a network. It is essential. Traditional control planes use a variety of routing protocols that determine the paths taken through the network and define the forwarding behavior of a network. And these are typically defined in a network using a variety of configuration constructs that are specified across the routers in a network. So a configuration error in one of these routing protocols can easily cause security or availability problems because of incorrect forwarding behavior. These traditional control planes are also rather complex. Each router in a network may participate in multiple what are called routing processes. These are different protocols that may be applied to compute the routes in a network. These processes may be implicitly or explicitly distributing information across each other. And in many cases, constructs like data plane and control plane filters are used to further restrict the set of routes that are computed by these routing processes. And because of all this complexity, the impact of errors may not be immediately apparent. Excuse me. So, for example, a couple of years ago in Azure's data centers, a misconfigured device and its failure triggered a latent configuration error in a bunch of other devices, leading to performance degradation in the Azure West region that lasted over for a couple of hours. All right, so given the complexity of control planes and given the importance of control planes to the well-being of a network, it is important that we understand if the control plane satisfies some key functional invariants. And examples of this include that a source-destination pair is blocked from communicating with each other, or that a particular set of flows are always isolated from each other, that they don't share links. Both of these invariants may be necessary from a security perspective, or that again for confidentiality or even for performance, the traffic between a pair of endpoints always traverses a particular middle box, such as an intrusion detection system. In some cases, operators may want to forklift their control plane and implement a new control plane, perhaps using fewer protocols to improve manageability. And in that case, we want to make sure that the paths the traffic takes in the old control plane matches the paths taken in the new control plane. Okay, so these are a variety of interesting invariants that are useful to verify that they hold for a network's control planes. The key point is that we want these invariants to always hold despite arbitrary infrastructure faults in the underlying network, because otherwise, like in the Azure case, you may end up with unforeseen security and availability issues. And the main challenge is that these invariants can be violated under some combinations of failures. So let me give you a simple example. So this is a simple control plane that uses what is called the OSPF routing protocol, Open Shortest Path First, which uses Dijkstra's algorithm, shortest path routing to compute routes. Here the operator wants to prevent T from talking to you. So OSPF computes the shortest path to go from D, B, and C between T and U. And so by placing these filters on the shortest path, we can ensure that T cannot communicate with you. However, when the DB and the BC links fail, the new shortest path that OSPF computes goes across the DC link, where there are no filters, allowing T and U to communicate with each other. Now, this is a simple toy example where a failure can lead to the violation of a particular invariant, but as networks control planes become complex and there are multiple routing protocols that interact in arbitrary ways and the number of such endpoints becomes large, verifying that these invariants hold for arbitrary sets of failures becomes difficult. So we'll use the term proactive verification to refer to the fact that we want to verify that these key invariants hold under arbitrary infrastructure faults, and such verification is useful because operators can quickly check their control plane configurations for satisfying these important invariants before rolling them out into the wild, and can catch bugs before they manifest in production networks. All right, so existing state-of-the-art tools cannot enable this kind of proactive verification. So if you look at data plane verifiers like HSA and Veriflow, Essentially what they do is they take a snapshot of the network's forwarding plane and they verify the snapshot for violation of invariants. Unfortunately, because you're only verifying a snapshot of the forwarding plane, you cannot verify that these invariants hold under arbitrary failures. More recent work has explored control plane verification. And here the idea is to simulate low-level message exchanges in routing protocols to generate data planes. So for example, you could say, suppose this link fails, what is the data plane that I would end up generating? Or let's say this other link fails, what would the new data plane be, and so on. Now, each of these simulations can be time consuming, and also exploring the exponentially many possible sets of link failures to generate all possible data planes can be even more time consuming, making this approach essentially infeasible to use. So how do we enable proactive verification of these control planes? So our main insight is that if you look at the invariants that I showed you, that hosts need to be blocked, or the flows need to be isolated, or they need to traverse waypoints, or that we want to test equivalence across networks, all of those are concerned with properties of paths, not the actual paths themselves. In order to say that T should not communicate with U, it is sufficient for us to check if a path exists between T and U. We don't actually need to compute the specific paths from T to U under specific failure scenarios. The second insight we use is that if you look at the set of constructs that are used in data centers and enterprise networks today, they don't leverage the full general set of control plane constructs that are out there. They basically tend to play with a limited set of control plane constructs. And what this means is that by focusing on exactly what it entails to verify these invariants, and by focusing specifically on the commonly used control plane constructs, we can hope to create a higher level abstraction for a network's control plane that is amenable for fast analysis. We no longer have to deal with the low level specifics and understand how to generate the data plane. Okay? So please feel free to ask any questions, because you can quickly get lost in this talk and I will just be speaking for half an hour. Okay, so our high level abstraction is called an abstract representation for the control plane, or an ARC. Essentially, given a network's control plane configuration, we derive from it a sequence of weighted digraphs which basically encode the network's forwarding behavior under all possible infrastructure faults. The structure of these digraphs is on the basis of the routing processes that are configured on the individual routers, and the edges essentially indicate the directions in which data can flow depending on the routing information exchanged across processes. The main thing about using ARCs is that whenever you want to proactively verify that the network satisfies certain invariants, it basically boils down to checking these digraphs for whether they satisfy certain graph attributes. So for example, if you wanted to check whether T can communicate with you, you basically check if they belong in the same connected component in this digraph. And the key thing is that when you're verifying this abstraction, you can completely ignore which specific protocols are being used, whether it is OSPF or BGP or whatever else, and how they are interacting with each other. You can basically deal with this abstraction and solve graph problems on top of this. Yeah, Anupam.
So infrastructure faults are just edge failures, all possible?
Yeah, exactly.
Are you bounding the number of them?
I'll get to that. So for now, for certain invariants, I'm allowing all possible edge failures, but for others, I'm going to bound the number of edge failures. Yeah. Okay, so for an ARC to be useful for verification, it needs to satisfy two properties. The first is that it should be sound and complete. Soundness essentially means that each of these digraphs corresponding to a source-destination pair must have all paths between the source and destination that can arise in the real network under arbitrary failures. And completeness means that the digraph should not include any paths that are not feasible in the real network. And if these two conditions are satisfied, then we can essentially make sure that the graph attributes essentially do correspond to the violation of invariants or not. So for example, in this case, there is one path between T and U that is reflected here, and there is another path that we want to be reflected in the corresponding digraph for the source destination pair. Yeah.
So I have two questions. So what you're doing is a form of abstract interpretation, for which there's a decades of PL theory about when you can define these kinds of abstractions and how they apply to the concrete things.
Yeah.
So the question is, have you tried to cast this in that light, and are there control plane protocols or features that sort of don't fit in because of the need to?
So this is exactly abstract interpretation, and I'm going to get into exactly which control plane protocols do fit in and do not fit in, and why not.
May I ask a second question? So if I had an invariant that involved sets of paths as opposed to single paths, it seems like this wouldn't fit in because the set of paths are all being put into the ARC model, and now I don't know if these two paths actually arise together or if they only happen independently. Is that one example of a limitation of this model?
That could be. We should take this offline. Maybe if you can give me a concrete invariant that involves sets of paths, I can think about whether that is checking that invariant is possible or not. So far, we have mainly dealt with individual paths.
A and B can happen independently but not together. So can that be verified in this model?
Possibly. Let me get into exactly the specifics. In a sound and complete arc, we cannot. So what we may also want for the arc is precision. And what this means is that in some cases, we may want to compute the exact concrete path that is taken between a source and a destination pair. And computing this could be useful because this could help generate a counterexample for an operator to act on the basis of. It may also be useful for equivalence testing. And in this case, it would be useful for the arc to be precise, which means that the min cost path that you compute on the arc, given some set of links have failed, must match the path that arises in the real network under those exact link failures. Okay. So for example, in this case, this is the min cost path between U and T, and that should be reflected in the underlying graph. All right, so the question is why weighted digraphs, and how can the simple abstraction capture all of these different routing protocols, and how do we ensure soundness, completeness, and precision? And I'm going to jam you through a couple of slides of heavy pictures to drive home these 2 points. So the reason we decided to use weighted digraphs is that most routing protocols in use today, like OSPF or BGP or RIP, essentially do cost-based path computation. So OSPF, for example, uses Dijkstra's algorithm, and BGP, although it doesn't define costs on the basis of individual links, it defines them on the basis of paths, and it uses numeric metrics like MEDS and local prefs to enable path selection, but they both basically do min cost path selection. And this is good because this allows us to create a single unified abstraction that we can use to do weighted path computation on, and hope to model multiple routing protocols using this abstraction. But there are a couple of differences that make our life interesting. The first is that different routing protocols operate on different granularity. OSPF operates on the basis of routers, BGP operates on the basis of autonomous systems, which are groups of routers. But luckily, the way BGP and other exterior protocols, gateway protocols are used in data center networks is more akin to OSPF, meaning that BGP is configured such that each router is an autonomous system, so we are kind of good there. The other key difference is that different routing protocols and different instances of routing protocols can use different currencies. So for example, a link with a cost of 4 may be more or less preferable than a path with a local pref of 4. So how do we actually bring them all to the same baseline to allow for uniform analysis? In addition, we must also account for a variety of other complexities that get thrown into the configuration of these control planes today. So for example, there may be policies that apply to specific traffic classes. Often different routing protocols redistribute routes into each other, meaning that the routes learned by one routing protocol are made available to another routing protocol. In this case, OSPF is redistributing into BGP. Or sometimes you may do route selection on the basis of administrative distance. This is the case where a single router knows of 2 routes from 2 different routing protocols, and you essentially end up preferring the route with the lower administrative distance, and that becomes your choice. And we need to account for this in creating this abstraction. And what this means is that determining the structure and the weights of these edges is complex. Okay, so to account for all of these complexities, we basically model our arc as a sequence of what we call extended topology graphs, or ETGs. We have one ETG per traffic class. A traffic class is a source destination subnet pair defined in the network. Each vertex in an ETG corresponds to a routing process running on a router. For each routing process, we have 2 vertices, one corresponding to the input labeled with the subscript I here, and another corresponding to the output labeled with the subscript O over here. So for example, for the routing process OSPF3 running on router X, we have these 2 vertices, and likewise for the routing processes OSPF3 and BGP1 running on router Z, we have these 4 vertices. The edges in the ETG basically correspond to how data would flow given what we know about exchange of routing information between routers and between routing processes. So for example, given how OSPF exchanges routing information between routers, we have this edge between X and Y on the top and a corresponding edge between the with input and output flipped on the bottom. And likewise, we have an internal edge going from the input to the output of a routing process internally, basically going from the input to the output of Y in this example. And to reflect redistribution costs, we have an edge going between two different routing instances that are residing on this router Z that essentially reflects how data could be forwarded based on information learned from a different routing process. So there are a lot of different other things that we can model in addition to route redistribution, OSPF, and BGP. We can model things like static routes, and essentially all of those things boil down to adding vertices and edges in this graph. I won't go into the details of this, but essentially for most of these constructs like OSPF, BGP, route redistribution, etc., we can prove that the digraphs we create are sound and complete. Now, edge weights are interesting. These are based on configured fixed costs in route redistribution and what are called administrative distances. And I'm going to go into that in a little bit of a detail over here. So for inter-device edges, if it's an OSPF process, we basically configure the edge weight to essentially reflect OSPF link cost, right? So for example, here there is a link cost of 2. We use that to configure the edge weight here. For BGP, we assume that there is unit cost per BGP hop, and this reflects the fact that in most data centers and enterprise networks we study, each router essentially pretends to be an autonomous system. Inter-device edge costs are more intricate. This is where we need to take route redistribution and other such things into account. And I'm going to highlight it with the simple example of the case where only route redistribution is used, where routes learned from one routing process are fed into other routing processes that are defined within a network. In this case, in this simple case, for vertices that correspond to the same routing process, we associate a cost of 0. And for vertices that go across routing processes reflecting route redistribution, we associate a cost that reflects the fixed cost of route redistribution. Essentially, what this fixed cost of 1 tells you is that if Z knows of a path through OSPF2 to go to a particular destination, then BGP should just associate a cost of 1 to that route, irrespective of what the internal semantics of that route is. This is a fixed cost associated with some route that the other redistributing routing process has learned. Now, this is not enough, because if we do minimum cost path computation on this digraph as I showed you here, the end-to-end min weight path may be incongruent with how these route redistribution costs have been defined. So for example, if you look at the shortest path through the top digraph, it has a cost of 5. And if you had, let's say, a different process redistributing routes into you with a fixed cost of 2, it may be that the operator intended that you prefer the route going through the first routing process, which has a lower redistribution cost than this other cost. But if you do end-to-end min path computation, then this ends up looking worse than this other path. So we need some way of mucking with the weights on these digraphs to ensure that the end-to-end path computation is congruent with how route redistribution happens. And the way we do that is by scaling the weights. We scale the weights in the redistributing routing instance down such that the maximum cost path through the redistributing routing instance costs less than any edge weight that has a non-negative cost in the redistributee instance. And what this ensures is that the paths in the redistributee instance are determined solely based on the weights of these local edges and on the redistributing route costs, and not on whatever happens downstream within the network. So you're completely absolved from what may happen downstream due to redistribution. So we can use a similar technique to take into account other things like administrative distance and combinations of route redistribution and administrative distance. But essentially what we can prove is that as long as the way routing processes are redistributing routes into each other forms a directed acyclic graph, our arc is precise, meaning that the paths it computes will match the paths that end up getting taken in the real network. Okay. All right. So Nate asked this question of what properties can you model using this arc. So we looked at a bunch of different protocols, and this basically shows that for most common constructs of routing protocols and various other things that are used, the arc we generate ends up being sound and complete. In order to generate precise arcs where the weights reflect the paths that are taken in the real network, we have to make some limiting assumptions. For example, we need to ensure that the route redistributions essentially obey this directed acyclic graph structure, and we have some other restrictions on the nature of how these routing protocols are configured. So the question is, how often do these properties arise in practice? Are there things that we are missing here that cause our arcs to be either not sound and complete or not precise in practice? So we analyzed about 314 data center networks, and we found that in all of the cases, the constructs used in those data center networks essentially make sure that our arcs are sound and complete, and they are precise for an overwhelming majority of the networks. In the 4% of the cases, essentially what's happening is that either the route redistribution costs they don't have this DAG structure, or that there is this other rule about congruence with the administrative distances that is being violated. But the arcs we generate are precise for the most part. Okay, so what I presented to you so far is a weighted digraph abstraction that is kind of free from the details of the underlying protocols, and I claim that you could use that for verifying various interesting properties. Yeah.
So is this an assumption or some implicit assumption about the nature of these topologies, like what topologies was this applied to? Right? I assume that some of these properties are trivial on a tree, for example, right? So are these topologies mostly trees? Are they something else?
These are data center networks so far. Most of them are hierarchical in nature, like a Clos topology and things of that kind. But the restrictions that we are assuming are on the control plane topologies, which is, if you look at how routing processes are arranged and how they distribute routes into each other, we need that graph to be a directed acyclic graph. And in general, if the underlying physical topology can be anything, but as long as the control plane graph has that property, we can prove those things about the arc. But the data center networks we analyzed tend to be hierarchical in nature, as we know, data centers are designed today. Yeah, pardon.
How expensive is it to generate these ETGs?
Yeah, I'm coming to that shortly. Okay, so here's a couple of quick verification problems that you can solve. Suppose you want to make sure that the traffic between these two hosts always traverses a middle box, and there are a collection of these middle boxes that are spread across the network. Here you see that there is a path that doesn't traverse this middle box. In order to verify this, we basically compute the ETG corresponding to that source destination pair. We remove all links that correspond to locations where the middle box already exists, and then we check to see if the source and destination are in the same connected component. Fairly simple, right? In this case, they are in the same connected component, so the invariant is violated. We can go one step further. We can say what is the minimal set of edges that we need to remove to separate these two things out, and that the operator can use to determine where to place a middle box to ensure the invariant is satisfied. We can check other things like always reachable within some number of failures. This is a question that I think Anupam you brought up earlier. And essentially here we need to make sure that the source and destination pair have at least k disjoint paths, which we can basically translate into essentially checking if the max flow on a unit weight graph is at least k, right? And essentially that's what we verify in this particular case. All right, so there are a variety of other things that we can check. These are the lists of invariants that we can check. So far, there are others here that I haven't listed, and they all boil down to some polynomial time graph property that we can check on the basis of these arcs. And in all of these cases, we basically, in order to generate a counterexample, we need the arc to be precise in order to give a concrete example of a path. And in the last case where we are checking the equivalence of two complete control planes, we also need the arc to be precise. All right, so let's look into how this thing performs in practice. So we have implemented this on top of Batfish. This was the tool that I referred to earlier and Ratul's group developed a couple of years ago. This is available on Bitbucket. I encourage you to download, and if you have network configurations, play with them. So again, the 314 data center networks we analyzed using this implementation using a single multi-core machine. So this is how long it takes to generate these arcs. So these are networks sorted by their size in terms of the number of links, and this is in seconds. And essentially what we see is that most of the time is spent in parsing these configurations, just determining that OSPF is running or BGP is running or route redistribution is used. Once the parsing is complete, building the actual ETG itself doesn't take as long. And this is building the ETG from scratch. Doing it incrementally ends up being much faster. And this is for networks that are pretty large. There are tens of devices in many of these networks, and many of these networks have hundreds of thousands of traffic classes. So this is a fairly scalable and quick thing that we can compute. So how quickly can we verify? Here is a quick result that shows verification of 3 properties: always blocked, always reachable with less than k failures, and always isolated. In the case of always blocked, we can verify even for the largest network for all sets of traffic classes in under half a second. Always reachable with less than k failures, we take a little longer because here we are checking max flow as opposed to connected component. Always isolated takes much longer because there we need to take pairs of flows and check to see if they are isolated as opposed to checking properties for individual flows. So there is quadratically worse time that it takes. We also tested Batfish to see how long it takes to check these properties, and in the case of checking if 2 hosts are always blocked, given let's say 2 or 3 link failures, we found that Batfish can take a couple of years to finish. So we are offering practical improvements in speed. Okay. All right, so I wanted to talk briefly about some things that may be interesting for the theory crowd here. So ARC as an abstraction is still preliminary. We don't know how general it is. I showed you a list of constructs for which it is precise, complete, and all of that stuff. We want to understand if ARCs are a good abstraction that covers all possible control plane constructs that are in use out there, which is a big open problem. But if you focus just on the situations where ARC is applicable, there are a couple of interesting issues that arise that I would like to talk about. The first is we could use ARCs to do automated repairs. So the problem statement here is as follows. You have a configuration, you generated the ARC for it, after analyzing that, you realize that there is a bug because some invariant was violated. Now you want to fix the configuration such that the invariant is not violated, right? You could do this by basically either taking an ETG and modifying edges, either adding or removing edges for an ETG or multiple ETGs. But the key challenge here is to find a minimal repair. One way to remove an edge from an ETG, for example, is just to add data plane filters, but you would end up spreading out data plane filters all across the network if you just keep using that as the way of removing edges. But perhaps there is a way of removing a peering link, which would be one edge that you remove from all the ETGs in common that helps you satisfy the invariant. The other interesting wrinkle here is that in some cases when you repair an ETG by, let's say, adding an edge, that repair has global effects because that ETG is common to all other source and destination pairs. And here you need to make sure that by helping one invariant be satisfied, you're not leading to violations of other invariants. So you need to do this repair minimally while minimizing side effects. Here's another interesting problem. ARC can be used to transition legacy networks into software-defined networks. Vyas already told us what these software-defined networks are. Let's say you have a legacy network with a bunch of legacy configurations. You can derive ARC from that network, and as long as the ARC is precise, a controller can use the ARC to determine the forwarding plane for the software-defined network. Each time a link fails, the controller refers to the ARC to compute the new path under the failure and installs that path within the network. Now this is a naive approach because each time a failure happens, you go to the controller, you do the computation, and you install new rules and delete old rules, and that induces a lot of churn within the network. Is there a way of pre-computing some of these backup paths that may manifest under failures by using the ARC that the controller has? Another interesting challenge is here we are assuming that the SDN network is using exactly the same topology as the legacy network. But if it were to use a smaller or a larger topology, how would you use ARC to do this transition is something that we don't understand. I'm happy to talk about this more offline if you're interested. And in the last minute that I have, I want to talk about one other problem that ARCs could be useful for. Which is to basically synthesize configurations of networks. So far we looked at verifying configurations that were given. Here, let's say your operator specifies an intent as Vyas indicated earlier on. Let's say you want traffic between some sources and destinations to traverse waypoints or to ensure isolation of flows or traffic engineering, whatever. Can we directly synthesize configurations? Now, the problem is that all of these invariants boil down to various ways in which paths are computed and interact with each other, and we want to basically use shortest path computation to somehow enable us to express those different intents. And basically distributed routing using shortest path routing is too difficult to program to specify all of these intents. So our current approach is, rather than directly synthesize arcs, we assume that we are given a set of input data planes, and from that we derive what we call a resilient arc, and then from that we compile configurations. Let me give you a quick example of this. Let's say the paths here reflect the paths that are provided, the colored paths are the paths that are provided by the input data plane. Here we want to assign weights to edges between different nodes in the graph, such that the path to the destination as corresponding to the minimum cost path should be the path that is used. In some cases, the minimum cost path between a source and a destination pair may not be the one that you want to use because it violates something like an isolation constraint. So you want to prevent minimum cost routing from picking that path, and you could achieve that by filtering that path out. So we use route filters as a way of taking out paths that would otherwise be chosen as min cost paths. But if you were to place filters all around, you end up with a network that is not very resilient. A failure happens and you don't have any paths here. So the idea here is you want to compute weights for backup paths such that A, the backup paths have higher weight than the path that you choose as the default between a source and destination, and they only kick in when failures happen. Okay? Solving this problem turns out to be hard, and again I'm happy to talk about it offline if people are interested. Okay, so that brings me to the end of my talk. This is the summary. Again, you can try out ARC, and it seems to be useful for a variety of different things in addition to verification. Happy to take any questions. Yeah.
I was thinking about an example you showed where the flow traverses the middle box. Can you expand your example to consider multiple middle boxes?
Chains of middle boxes? Yeah. We can do that. So basically the way we enforce the chain is we take one middle box from the chain out, and we see if the middle box before can reach the middle box after. It should not be able to reach. There should not be a path because you want the path to go through the intervening middle box. So we can enforce middle box chaining that way.
So if you do it incrementally?
Yeah, we take one thing at a time and make sure that there is a sequence of middle boxes that are used. So the complexity is the number of middle boxes that are involved in the path. Yeah.
So I have a question about the properties that actually verify.
Yeah.
I think the things you showed was is it reachable? Is it blocked? And can you also verify after this failure the number of hops between these hosts to be less than n, or
Yeah, such quantitative things are a little harder for us to verify. We need precise arcs in order to be able to do that. And because we can ensure precision only under a restricted set of assumptions, we can't answer those questions in general networks, right? Because the number of hops that are used depends on the actual costs associated with the edges, and for that we need a precise arc. So yeah, so some questions we don't really know if or whether we can even address using arcs.
Very cool stuff. I think my question is more about the synthesis stuff. Are you assuming that the networks, the underlying, so there's one free variable here, right, which is the operator gets to pick the protocol they want to run. So in the synthesis problem, is that an input, or you will decide?
Yeah, so that's actually an input. So currently we are assuming can we do it just with OSPF? Okay, and even there the problem seems hard. Now maybe if we were to restrict it to some other sets of protocols like BGP, it can become slightly easier. But if you were to use a mix of protocols, I don't know what would happen there. So right now we're assuming it's OSPF. Yeah.
So you mentioned you're using this as a tool for verifying SDN control programs.
No, it's not for verifying SDN control programs. It's basically for transitioning a legacy network to an SDN network.
Okay. But to do that, I think you'd have to, so for my, if you wanted to verify SDNs using this, you'd have to basically run the control program through all possible paths and all the configurations it could produce to build your arc. And there really could be arbitrary code. It's just Java code or Python code. So building the arc would itself require an expensive simulation or symbolic.
Let's talk about this offline, but what I'm implying is just as an intermediate tool to move from legacy to new.
So why don't you have to do the same thing for these other control protocols? So when you showed us how to build an arc, you sort of built nodes for each of the different routing processes running, and then you drew edges. Why don't you have to look at things like ACLs and the different policies and configurations? Why aren't those policies being interpreted to build?
So they are, I totally elided those issues. So we do take into account ACLs, route filters, static routes, all of those things. I just presented a subset of those. The way an ACL would come into play is by taking an edge out of our graph.
So if there's edges that are sometimes in the data plane config under certain scenarios and sometimes not there, would the edge be there or not there?
What would be an example?
Spanning tree. So you spanning tree and OSPF on top. The spanning tree edges change every time you do this. So it seems like the complexity should be the same as Batfish for that one.
Yeah.
That could be, yeah. That could be. That's a good example. And I don't know what we would do for spanning tree. It's not in the list of protocols that we can model. I don't know what arc would look like in the case of spanning tree. Good question. Yeah, Sujata.
So maybe this is just a follow-up from what Nick asked. Do you see applicability of this to hybrid operation in SDN?
Maybe. I mean, I think it's a little. I mean, the way I pitched it is purely from a transition point of view. I mean, once you transition a network into SDN, you may want to do other things with it. And you may want to figure out how that composes with other stuff that you may want to do in your SDN. And I don't really know how ARC would fit into such things.
I think the way to, maybe one way to, we haven't thought too much about it, but just thinking on the fly. I think one thing ARC gives you is a high-level representation of what a conventional network is trying to do. And so if you wanted to do hybrid, I think it could be a starting point. And suppose you already had an SDN verifier. Combine that with the ARC representation so you don't have to deal with the low-level details of your conventional network. I would say one kind of just straightforward combination if you already had ARC and some technology to do pure SDN reasoning.
Yeah.
Well, I maybe missed something, but you were talking when you're trying to see if there was a barrier, there could be no path between a set of nodes and another set of nodes thinking of the quadratic work. How come the standard trick of kind of a super node for each side, maybe just checking for each, from this group to anything in that group, from anything in this group backwards?
Possibly. I mean, this is a very naive implementation. I'm sure there are more efficient ways of checking isolation, for instance.
Okay, so
but, yeah.
What would it take for you to sort of reapply this in sort of a carrier network where you have, the transport layer is not just a single link, but that's another network, and so you have a hierarchy of networks now. So when you have the layer 3, it's actually running on top of optical layer, which is another network, which is again running protocols like OSPF.
I mean, my feeling is that we may be able to model that. Again, it depends on exactly what protocols are used and how they are configured. Let's assume that matches with what we are seeing inside data center networks. We should be able to model that. I'm assuming that even the diversity doesn't mean that there is something different happening on these different multiple optical paths that are available. As long as that is the case, we should be okay. We should be able to model that. But there may be other aspects of control planes that are used in carrier networks that we may not be able to model. I would have to look at data to be able to give you an answer there. Okay, thank you.